Good, thank you. Okay, well, Happy New Year, everyone, and welcome. Thank you for attending our College of Natural Sciences webinar. My name is Allison Sherwood. I'm the Interim Associate Dean for the college. And through our Pilina webinar series, we are hoping to showcase some of the world-class research that happens in the College of Natural Sciences as well as around the Manoa campus. And today, our presentation features Dr. Monique Chyba, who is a faculty member in the Department of Mathematics for the College of Natural Sciences. Dr. Chyba joined the Department of Mathematics at UH Mānoa in 2002 after a journey that took her from Switzerland, where she got her PhD, to Paris, Harvard, Princeton, Santa Cruz, and finally here to Honolulu. Dr. Chyba's main research area concerns the development of geometric methods to solve optimal control problems. Her research is oriented towards applications with a special emphasis on motion planning problem for unmanned underwater or aerial vehicles. Modeling and computational or data-driven research has become a larger focus over the last few years for Dr. Chyba. In particular, with a group of colleagues and students, and in partnership with the Hawaii Pandemic Applied Modeling Work Group, or HIPAM, they have developed models and mathematical tools to analyze the spread of COVID-19 during the current pandemic, which is what she's going to be talking about today. And so without further ado, I'd like to turn over our time to Monique for her presentation, which is entitled Pandemic Prediction Modeling Gone Viral. Thank you for joining us, Monique. And we'll have you unmute yourself to begin.
All right, thank you, Alison. I appreciate the introduction. It's my great pleasure to be here today and reflect on almost now, it's really sad to say that, but 2 years of pandemic modeling. I watched the previous talk and I'm very honored to be invited as a speaker in this wonderful series, and I'm very privileged to be able to talk about mathematics. So indeed, we're going to have a little bit of a look into the pandemic and the modeling. So to give a little bit of background, when the pandemic took the world by surprise in 2019, about every mathematician started to look at the COVID data and disease spread modeling. And I won't say every STEM inclined person started becoming crunching the data and trying to fit them and to make forecasting. And this situation came with a lot of advantages and inconvenience. First, it had a lot of stimulating activity and accelerated progress because so many people were working on that. But also, it came with extreme scrutiny and criticism. And I have worked on various applications before, but the pandemic modeling really took me to the edge, and it's been quite an experience, right? It involved urgency, which typically as a mathematician we don't face. And it also was the most concrete bridge between the reality and the theory that I ever experienced. And it came with a lot of media attention and visibility that as mathematicians, we're definitely not used to have. So we're not well equipped to deal with, but we're trying to learn. All right, so here is a little timeline. So you can see the slides. We're on slide 2. You can see the timeline of the pandemic. Okay, so that's not the first pandemic that the world is experiencing. So plague was, it did other pandemic, which were usually more localized because people did not have the ability to move as we do now. And then the influenza. So the current death toll for COVID is 5.6 million, which is way under the 1917-1919 influenza pandemic, but above the one that we had in 1957-59. So Hawaii has a non-easy history with respect to foreign disease, with the arrival of Captain Cook that was catastrophic and devastating impact on native population, which were estimated to have been then decimated to about 90%. And even though they sort of bounced back starting around the very early of the 20th century, the damage was done. So it is always a dear discussion to talk about the pandemic. And at the time, some of the responses that happened for the prior foreign disease arriving into Hawaii, the King Kamehameha III, he established the Board of Health, and he was sort of ahead of his time because the United States wouldn't form their own Department of Public Health until almost a decade later. And they passed, so that board passed many regulations like it's doing now, like where people had to keep their horses tied up, the incoming vessel had to be cleaned and inspected, and then they were basically having the same rule as we have now, where you have to wash your hand, etc. So then there was at the end of the 19th century, the smallpox pandemic, which lasted for 5 months, and it claimed at the time about 300 lives. And Queen Liliuokalani, she took actions, and they can be, you can see them on the screen, and they may seem like extreme in many parts of the world in the 19th century, but they made sense. Because they happen on an island that has been already fatally impacted by epidemics. So there were over 800 cases, and the quarantine at the time that she implemented was viewed as a success because the pandemic didn't reach the other island. So we're going to look a little bit, now we're going to, that was just a little bit of a background, and we're going to transit to the COVID pandemic and try to see a little bit at the timeline of what happened in the world and then in Hawaii. I will go, of course, into the modeling and the mathematics, but I'd like to give a little bit of a background before. And today, because the audience is very broad, I won't be extremely technical in terms of the tools that we have used, but this is what you see is the timeline. So it was clear in December 2019 that something was happening in China. And in as early as January 2020, it was identified out of China. And in March 11, 2020, that's when the World Health Organization declared COVID-19 a global pandemic. And at the time, we had over 100,000 cases and over 110 countries and territories that were identifying the pandemic. So you can see on the top right now we are at 355 million cases, 5.6 million deaths, and you have also some information about the vaccine. So this is the timeline for Hawaii. Hawaii is very unique. It is very special geographically, ethnically, and everything. So it was very important to put a lens on what would happen on an island and on an archipelago like in Hawaii. So that's the timeline. And it was March 6th when the first case was actually identified. And it was followed at the time by a very aggressive lockdown and strict quarantine for travelers. The death toll now is a little over 1,000 people in Hawaii. So we are higher than a typical year death toll for the flu. In 2017, there were about 637 influenza pneumonia death and 542 in 2018. And it peaked at a little above what we are now in 1,500 deaths in 2019 for the influenza pandemic. And it came like a year about, the peak was a year about what happened in the other islands. So in response to that, this is a slide that I added. So that's shows that just to put things in perspective and where Hawaii is in terms of the other states. This was a few weeks ago back, but it is one of my graduate students. He made that plot. He's here today. So it shows you that the state of Hawaii, it gives you a perspective on the number of days, on the number of, the horizontal axis is the number of days that have elapsed. No, the vertical axis, and the horizontal axis is the percentage of the population that has been affected, that has been detected. So we have this is the first, we have to be very careful with data. That was one of the big issue, and I'll talk a little bit about that, about the availability of data, because this is always dependent on what data are shared, are available, etc. So in response to the pandemic, in the early spring 2020, Dr. Victoria Fan, she's the director of the Pacific Health analytic collaborative, and she's an associate professor at the University of Hawaii in public health. She formed what Alison mentioned before, the Hawaii Pandemic Applied Modeling Work Group. And the idea was that we would gather together the expertise that we had. And it was a voluntary partnership. There was epidemiologists, health professionals, data scientists, which might be scientists from different fields, not necessarily mathematics. And we got together in order to try to look at what was going on. So since then, we closely monitor COVID transmission data, examine influence of multiple policy intervention. We maintained some COVID forecast. We communicated to the public. We provided scenario decision to some government institution here in Hawaii and so forth. So this is the website. There is a website. We've done community meeting. And also this is the, that's not as of today. So do not look at the curve like we're descending like this right now. That's a snapshot that was taken where we are coming down from the Delta surge. So this is updated on the website on a sort of a weekly basis. So then at the same time, as this was happening, we have, with my colleague Alice Koenig, she's also at the University of Hawaii, supercomputer, Maui supercomputer, and now at the Hawaii Data Science Institute and part of the Information Technology Service, and Associate Professor Yuri Milejko from mathematics. We submitted a proposal to the National Science Foundation that was really tailoring to contain population archipelago like island and that are geography isolated. That was really understanding, because very often they're left out of the general study that we see in the paper. So it got funded, and then we started forming a team in July 2020. And here, so you have part of the team. The team has been like the pandemic, it's been evolving through, because we have students that works. And I know a lot of the talk were involving space exploration and planets and so on. And I have my stars too in that research, and that's definitely the students. They've done like a tremendous work, and they've learned a lot, and they've been instrumental and to everything that you're going to see that is going to be explained today. All right, so let us go a little bit more into the topic. And epidemic forecasting, it's still, we have to see it a little bit in its infancy. It's a growing field with a lot of potential, but it has there are two aspects that are really, that makes it really difficult. It's the availability of data, and then the changes in human behavior and pathogen. It is very difficult to understand what a human is going to make as a decision, how they're going to behave. And that's basically what you have to do when you model a pandemic. So it is harder than weather forecasting, even though we know you cannot forecast weather. Nobody comes to someone and say, hey, what is going to be the weather in 4 months? Because I'm planning to take a vacation in Hawaii, and I really would like to know, well, it's always sunny, so that's maybe not a great example, but like I'm planning a vacation somewhere, tell me where it's going to be in 6 months. That's not a question. People are used to not ask those questions, but we were asked those questions about the pandemic, where it is going to go. I had people coming to me, hey, what do you think? Maybe we want to do a conference in 8 months. What do you think? And that was extremely difficult. So if for a pandemic, we need to forecast the behavior of people, which make it fairly impossible. So, but by now everybody has heard about flattening the curve, right? That's without a doubt the success story in epidemic modeling. And we have also that R0 number, which is the basic reproductive number. It's the average number of people a newly infected person will infect in a population where everybody else is susceptible. And then it depends on the behavior of the population. And then, so it depended on mitigation measure, on mask wearing, the length of time a person is infectious, etc. So if for the flu, we can assume that this number is static. That was certainly not the case for COVID. That made it challenging as well. So what can a model do? And I think there was a lot of misconception about pandemic modeling. So again, it's very difficult. okay? But it's to make a model for a pandemic, but it's even harder to use it properly. And that's why there was a lot of criticism and a lot yeah, it was a very controversial issue. So first, there is a very limited data. And as I said before, people are very complicated. So, but it is more than just flattening the curve. And I hope I'm going to be able to convince you today that while a model is not an oracle, it can provide a lot of good and a lot of information that is useful in going through a pandemic. So for instance, it can understand the past. It can create scenario, what if we assume those non-pharmaceutical intervention, which one is going to impact best the model? We can do sensitivity analysis to determine the impact of some variable. Who should receive the vaccine first? What is the optimal strategy for vaccination, depending on the cost? And then the other question is, what can they do? Well, unfortunately, a lot. And what they cannot do is predict accurately number. And this is what people wanted them to do. So that's why it was so difficult to communicate the result, and they could be misinterpreted. So in the pandemic, the relative importance of the model parameters has changed over time to account for changes in social distancing, mask wearing, vaccination. Also in the early pandemic, there was a lot that wasn't known about the virus, like exactly how it was transmitted. So the very basic information we need to have in order to model the spread, like did it transmit it through air, fluid, surface? People were washing their groceries. Like in China, they're still washing the mail that is coming from abroad. So it was like a lot of confusion came and a lot of uncertainty. And then that means a lot of parameters were widely varying. And because we have an exponential phenomenon, a small perturbation can bring to a big difference. Okay, so this I said, so I'm not going to spend too much time on that, but a pandemic is people driven, and it's really hard to understand what happened. And it's not just that, it is people driven. That means like, I'm going to go into that, and our different island, our different counties in Hawaii have responded in a different way to the pandemic in terms of the spread. And it's because people are different, it's different ages, it's different ethnicity. It is, and all of this makes a big difference into how then that spread. So here that was, you know, people wanted me to be accurate. And I think this was the most accurate answer that I was able to say when people were asking me. They were asking me, what is going to happen? Are we peaking? Are we curbing? Are we going to go down? What is going to be the top? Then I don't know. I actually don't. I cannot give you, I can do trend, I can do scenario, and I'll show what we've done. And unfortunately, what has been deemed our success story is, in my opinion, really not a success story, but I'll go into that a little bit later. So let's go more into the modeling. So it is fairly recent when you compare to physics, the law of physics, and like sending something like, again, we had a lot of talks about space exploration, and we have satellites that go really far away. We have a Mars rover on a different planet, and people went to the moon, and you're like, that should be much more difficult, but the law of physics have been, they're not people dependent. So it is actually much more robust and easier to be able to model going into the space. And people have been working on that for much longer than we have been doing on epidemiological modeling. And Daniel Bernoulli is often seen as having provided the first mathematical model in epidemiology, and he was followed, it's not here, but by someone named Jon Snow, which is not from the Game of Thrones, but he found the source for a cholera outbreak in 1855 by doing some modeling. And then surprisingly, a lot of the core of what we're using now in mathematical modeling came more for public health physician rather than a mathematician. And in particular, Sierra Ross received the Nobel Prize in 1902 for his work on malaria and understanding the transmission between the mosquitoes and human. All right, so I'm going to go more now into the core and talk about the models that we have been using. We have been primarily using two different epidemiological models. So the compartmental model, also called like differential equation-based model, and then we have agent-based model. So I'm going to go into both. They're structurally extremely different, and it was important for us to work with two structurally very different models and compare the outcome, so that like the prediction or the forecasting or the fitting that we're doing was not biased by the type of the model and how it was constructed. So that was a big work that we have done at the beginning. It took us like about a year in order to actually really develop those models, a year and a half, to really calibrate them to Hawaii, etc. So compartmental epidemic model, it started with the work of Kermack and McHenrick with the SEER model that was there on the right here of your screen in the early 20th century. So again, very, very recently, it's like we're doing baby epidemiological modeling at this stage. And once we get out of that emergency and that pandemic, I suspect there will be a lot of work and a lot of improvement into the model, because we'll be able to ask the right questions. So the idea is that people then are divided into compartments. You aggregate the population into susceptible, into infected, and then into recovered. And then the models, they were a little expanded in order to create like the exposed state, which we used in our model as to describe the asymptomatic. So this is what like the typical SEER model that was developed, and the model that a lot of people worked with. And what we did very early in the pandemic is that we broke that model in two pieces, and it took a lot of time, right? We generalized the model. The population was divided further down into general community healthcare workers, and then we started including vaccinated people. And now we have two different variants that are competing, the Omicron, the Delta. So that is not even here, but then the diagram becomes tremendous. And in Hawaii, something that was not addressed in almost any paper or any model is the existence of traveler and the importance that they had. So on the right, you see the little diagram, and it gives some information about that and how we included them. And then we broke down like the asymptomatic, it can go during 14 days. And then we broke also the infectious people. We have 14 stages to be asymptomatic. We have the infected individual. Once you have symptoms, you go through 5 stages in our model. The first 2 are every day, and then it depends how you're fighting. It depends on your immune system. You can stay longer in 1 or 2 or in 1 stage or a different stage. Then we have probability to move people from just being symptomatic into hospital, into isolation, into quarantine. So all of that had to be broken down to get eventually a big model that then you can translate into equation. And the key into the equation is the hazard rate. That's about as much as I'm going to say, right, about the mathematics. Then I'm going to go more into how we were able to use all of that. But I think it's important to just have an eye. People tend to tell me, oh, don't put any formula, you lose everybody. But I'm hoping I'm bringing everybody in, because those formula are actually the core of what is happening, and they're beautiful. I mean, that's okay, that's my perspective on them. So here you have the equations, and again, it's just a fraction of them, and the hazard rates that is here, that lambda c is the one that describes how all those compartments work together, and what are the probability that this one is going to infect this one, etc. I know it's a lot of information, it's quick, but it is how we develop the model. And then the other model, we worked with the Institute for Disease Modeling, which is part of the Bill and Melinda Gates Foundation, because they were developing an agent-based model, complete different approach. In compartmental model, you assume people are aggregated, like population are aggregated into compartment, and you look at how one compartment interact with another one. Agent-based model, so I will come back to that, okay, but yeah, you have the picture. Yeah, you have the network. So an agent-based model is a network, okay, where every node is one person. So you have a lot of nodes. So as you can imagine, and then every time you have to reevaluate the status of everyone with respect to everyone. You have contact networks, and in their model, the Institute for Disease Modeling, they had 4 types of control of contact. It's the same as household, you work together, the community, or you go to school together. And then, so what you do to every node is a person. That means now I can associate easily a demographic, the age. I can associate easily whether the person is vaccinated. I can associate easily whether, if I have that information, whether the person is actually asymptomatic, and I can follow individual, which you cannot do with compartmental models. So very different. Okay, so now there is each model has perk and difficulties, right? So the popularity of the agent-based model, that's very new, right? We're talking at the 1990. Why? The reason is that they're computationally very, very expensive. Okay, and here we use the Alice Koenig, which is in supercomputer. She gave us access to the National Energy Research Scientific Computing Center facility that is operated by the Lawrence Berkeley National Lab. And that's what we use in order to run the model that was doing the agent-based. So they became popular, but it's, again, even much more recent than the SEER model. So the complexity, conceptual complexity, thumbs up for agent-based. It's much easier. I just add, instead of having 39 attributes to a node, now I have 40 or 45. That's very easy. For the compartmental model, when you change the conceptual complexity, if you add vaccination, you add a new variant, it's much more complicated. Data feeding, thumbs up for compartmental model. It is there, you can really use some techniques like classical gradient descent based optimization method, etc. And you can do that because you can compute the gradient with respect to the parameter in the compartmental model because it's easier. Doing that for the agent-based model is extremely difficult. So we capitalized on the fact that we had the SEER model in order to initialize the agent-based model. And here what you see is that in blue, you have the compartmental model, in green, you have the COVASIM, and we see that they are there fairly well. And what you have to really understand is that we were extremely careful not to overfit. Okay, you have a lot of parameter, and I can say, oh, okay, I'm going to change transmission in a continuous way. So then I can fit anything you give me, right? I can fit any spread that you give me for Hawaii. So we were very careful to match the fitting that we were doing, and when we were allowing to change some of the parameter to the mitigation that happened, and that it was aligned with Hawaii. Otherwise, again, you can do pretty much whatever you want, and that's very dangerous. So now that we have our 2 models that they agree, we did a lot of benchmark scenario and tried not just by fitting, but that looking at what they would forecast. We felt fairly safe, and we started looking at the Hawaii Island. So a lot of heterogeneity, and that's what I'm going to go now. So this is like, I don't know if you remember, but this is just the timeline for Hawaii from March to September 2020. It does not even go past 2020. And it was like every 5 minutes, something was changing. You wear a mask, you don't wear mask, you can go to the beach, you cannot, you can go hike, now you stop hiking, you can just cross the park to go to the beach and go on the water. And it was just like, that was really confusing, really difficult, and it made it very extremely frustrating for the people to follow what was happening. And on the other hand, we didn't really know what was happening, so it's understandable that there was a lot of confusion and a lot of different information that were going out, but that definitely something that should be prevented in the future. So here you see, that's the spread of the evolution of the pandemic on the 4 different counties. So on the left up, you have Honolulu, on the right up, you have Hawaii. That's done by the SEER model that we have. Pratik, he's also one of our graduate students. He's been working really relentlessly on making those all like most of the plot that you're going to see today. On the bottom left, you have Maui, and on the bottom right, you have Kauai. So Kauai is a little younger because Kauai didn't have a lot of cases for a very long time. And if numbers are very small, then modeling cannot happen. So it is here you can do a lot of eyeballing. So what you have in red is when transmission changed. Okay, and again, it's aligned with the mitigation measure. When you have a lockdown, then transmission, much less interaction between the people, transmission is going to go down and the curve is going down. And then, so we had to adjust our parameters and estimate them based on like the model was estimating what was going on. So you can eyeball a lot of information here, but still difficult, right? And the island were fairly similar in terms of the evolution of the spread until October 15, 2020. Why so is that then traveling started coming back to the island. And we have different, so this is, you can see this a little better. We normalized all the curves by the maximum value in each county, and then we plotted them on the same graph. So in red, you have Honolulu, in dark blue, you have Maui, in black, you have Hawaii, and in light blue, you have Kauai. And you can see that after the safe travel began and we started having an influx of travelers, then the curve started to defer, right? So we wanted to put like mathematically to analyze that a little better. So we use some statistical methodology in order to quantify the difference between the evolution of the spread. We used a permutation test and computed p-values. And this paper is currently under review for PLO1. And then it really highlighted the fact that the different counties are different. So we need to really put a lens on each island separately. And this was motivated by the fact that at first we would get a bulk of numbers. And because Honolulu has the majority of people living, then it was completely shadowing what was like, it was putting like a dark cloud on what was happening on the other island. We couldn't see. And the other island were much more vulnerable to, for instance, super spreader event, because there are much less people. So if you have a super spreader event on another island, it's going to magnify much more than it does on Honolulu. So that was one of the work that we have done. And oops. Okay, and then we were thinking, okay, let's compare to other location. So that became a little more difficult. So we choose Japan because you know, we have a close connection with Japan in terms of traveler, in terms of ethnicity as well. We choose Iceland. It's also, we choose island, right? That makes sense. We choose Iceland because it's another island that is isolated and that had pretty strict restriction on traveling. We use Puerto Rico because the climate is sort of the same than we have here. But we couldn't use the same metric than we used for our island. And the reason was that the pandemic was on a different timeline. Things did not occur at the same time. So if we used what we did, the norm that we used and the comparison we did between the island, it was not leading anywhere. So the metric then was used using what we call merge tree, which are qualitative structure, and they can be seen as topological descriptor of function. So we looked much more at the qualitative outcome of the function, right? We construct them by tracking how connected the component of the sublevel set appear and merging them and constructing them on the right. So what you have on the right is exactly the same as like what you have here is the same as what you have on the right for the Hawaii County. It's just in a different language, in a different, we use different tools, mathematical tool to represent it. And it came that Honolulu was closest to Iceland, that Maui was closest to Maui. No, Maui was closest to Japan in terms of their evolution. And then the Big Island closest to Puerto Rico in terms of qualitative structure. So we're still working on that. We were working on that and trying to develop really a nice tool, looking at all the states, but then Delta happened. So it's still there, but it's going to take a little longer. We were looking also at the geographic distribution of the COVID, because at some point the DOH on their dashboard were providing that information. So we could now, I feel like one of the students that was doing that, I don't know if she's here today, but she was pulling by hand out of the dashboard the numbers and putting them into a spreadsheet because they were not available in a different way. Like, keep in mind, all the work that we have done is done on public data. We had no access to any type of data that you don't have access neither. It's solely public data. So we had to work with those limitations. At some point, they were giving the zip code information. And then it was very useful because we were like, oh, okay, we're going to construct again a network and see what zip code is fitting what zip code. But then that information was not given anymore. So that sort of died. So then we also, another way that we started another information that that the model is doing compared to just data that you see on dashboard is that it computes what you cannot collect. Like, for instance, we don't know how many asymptomatic people are because you're not going to ask the entire population to test every day. So you cannot figure it out. They don't have symptoms. They don't know they're asymptomatic. They're transmitting it, but at the same time, there is no reason for them unless it's absolutely clear that they were exposed to someone to just get tested. And we would have to test the entire population to have a good background. However, the model is computing the asymptomatic population in order to fit the data to the symptomatic, to the detected daily cases. So here we started, like you can see, we started plotting total symptomatic over total asymptomatic and getting those curves, right? And what was nice is that we have also, I don't have those in terms of the Omicron, but we can see a difference as well. We can see here on the left, that's for Honolulu, and then for Hawaii, and I'll mention that. You can see those curves, which are almost closed loop, and they all come back to the same point, which is actually not the origin. They do not come to 0, 0. And we sort of, like, the next step that we're going to do is that we're going to try to understand if that is an equilibrium for the dynamical system, which will in turn be the endemic equilibrium that we want to understand, because that will be where eventually we would be, and we want to control that. But for now, that's still a question mark. So we have those loops. The first one here, we're done with the alpha variant, the one on the left, the blue, green, yellow, and then Delta came, and hop, we saw that we had the red curve. That means we had much more asymptomatic for pre-Delta. For every symptomatic, we had about 5 asymptomatic, and during Delta, the ratio was much bigger. So they were, and you can say why. Was it the virus? It was mostly the vaccination. We had a huge increase in vaccination, and if you're vaccinated, your chances to be asymptomatic with Delta were very high, and therefore that's why we had much more people infected, and the tip of the iceberg, like what was under the tip of the iceberg, became very, very big. Okay, but again, that's something that we were able to determine using the model. Then I will go into the Delta journey and the Omicron journey. So for mathematical modeling, the tendency has to be, was that, the Delta journey was a failure for mathematical modeling, and the Omicron journey was a success for mathematical modeling. And I deem the exact opposite, and I'm going to try to explain why. Epidemiological modeling are meant to be proved wrong. That's the entire purpose of epidemiological modeling, is to look at where we're going and then take action to not go there. And that's what happened with the Delta. And that's not what happened with Omicron. So surprise, the model, we've been working with it for 2 years, was fairly accurate, and we didn't take action, therefore we went exactly where we were. However, for the Delta, I'll go and I'll show you a little bit of what happened. So first, what is really difficult and where the model can help is, are we on a surge, right? Are we just oscillating around like an equilibrium where we are? At the beginning, it's an exponential growth. So the exponential growth does not grow it grows exponentially from the beginning, but it's fairly flat at the beginning. So you don't see it. And that's why in the summer, in July, this is as soon as July. We were seeing it. We were seeing in the model that something was happening. However, it took a little bit longer, as you know, and the month of August and a surge to realize that, yes, we were on that slope. So we were comparing July 2021 and to July 2020. And even though it was fairly clear at the beginning, it was clearly on a different exponential surge. So we could at that time, the optimized transmission rate was twice. And one of the reasons was also the fact that we had high vaccination. So the transmission rate was actually estimated by the model as being very high. And then for Hawaii County, it was even bigger. Okay, the Delta was devastating for Hawaii County. That was where it was sort of in control until then, and then the Delta came in and created the largest, not like it comparatively to the size of the population, to the density, the largest surge. So then we went into the simulation. We started looking at variant. They started disclosing some genomic sequencing started to take place. So we had a little bit of information of how much Delta versus how much Alpha. And then we started plotting that and trying to understand. And it was very clear that Delta was overcoming Alpha extremely quickly. So we started doing some forecasting, and this is the forecasting that sent the media and everybody into sort of, I don't know how to say, but in an alarming stage. It is when back in very early, end of July, we predicted 3,000 cases in August, or that was early August, 3,000 cases in October, if nothing would happen. You can see look carefully at the plot, right? The red dots were actually the cases, the actual cases. The dark green was represent the fraction of vaccinated, of asymptomatic, and then the light green, the fraction of symptomatic people. Oh no, it's the vaccinated, sorry, the light green is the vaccinated and the dark green, the unvaccinated. More like, of course, the model predicted that mostly unvaccinated people would start developing symptoms, which is what happened. So, but we predicted 3,000 cases, and there was a lot of brouhaha about that. And then we got a lot of backslash, like people said, oh, the model is wrong, but because what happened, okay, so this is at the time of the model, we estimated that about 16,000 infected people were actually in Honolulu, just like going around. Those were the asymptomatic individual, and that was for Hawaii County, right? We were doing it for all the counties. So now, if you look the simulation for September 15, so we were predicting, again, remember, we were predicting 3,000 cases by October, by early October. Then simulation of September 15 came, and in between, things happened, action were done, and we started going down in between, okay? Oops, sorry, I'm just moving things a little around. All right, sorry. So we started taking actions with respect to that, and that started in the month of August. Remember, the governor asked people not to travel. There was gathering restriction, etc. So cases, and people started really like acting as a feedback. That's another component that we are going to study once the emergencies goes down, is how the public feedback control is a very known field in control theory. And here the largest feedback that we have is the public. If you see big numbers, then you tend to be more cautious. If the number goes down, then you tend to be more open and go out and then put transmission more at risk. And it's a perfectly okay behavior. But it does play a role, and it played a big role in the Delta, so it went down. What I'm trying to say is that we didn't go to the 3,000 cases. So then people started to say, oh, the model is wrong. They predicted 3,000 cases in early October. It didn't happen. They don't know what they do. And let's just not listen to modeling, right? Now I'm saying that, but there was a lot of support as well, right? Of people that understood exactly what happened. What happened was what was supposed to happen. We were showing what was the potential on the exponential that we were, and then action were taken to not get there. Okay, so for me, thumbs up. Delta experience, thumbs up. Then that was, and that's also at the time where the Kauai fit started, because unfortunately they started having enough numbers. So then this is what the modeling was giving us as of November 21. Okay, so it was going down. Everybody was very happy. We were nailing it, and cases were down. They were sort of plateauing. Is it what we eventually want to look at the endemic equilibrium? We'll see. But then look, there was something happening here, and oh, that's not this. Okay, let's see. Okay, so we did that one, and it's not the right plot. I'm really sorry about that. But we started seeing already, like November 14, a deviation from those loops. That means even though like, if you look at the daily cases, it looked like that, the model was telling us something was happening in mid-November. And that something was right here. That was Omicron. Because afterwards, the model we worked, we tailored it, the parameter, we calibrated the parameter, and the Omicron started well before like community spreading started. We estimate about mid-November, which means that it came into the island about sometimes in sometimes in October. So difference between Delta and Omicron, and for the modeling, it's been quite a different journey. Because then we were starting to model two competing variants. So we added that into the model. It has like the Omicron, so you have the more biologically oriented people, you have that nice picture that shows how much Omicron had mutation with respect to the Delta. And then we started looking at the region where Omicron was happening and creating the surge, which was South Africa. Then you have the Netherlands in the middle, and on the right was Switzerland, I believe. So December 5, what happened? Oh, here is the plot that I wanted to show you. December 5, it was clear, like that shows, you see that green purple beginning of a loop, that was the Omicron, and it suggested that it started in November 15. So it was already picking up that we were not in good shape. And then we started doing some forecasting. However, it was really hard because on Omicron, is it 2 times as much transmissible as the Delta? Is it 3 times as much transmissible? Well, you might think like the difference between 2 is maybe not that big, right? It's just you add 1. Well, it's very big on an exponential phenomenon. If you do 2 or 3, if you put a 2 or a 3 into the model, then you get a complete different, you get an explosion if you get 3, and I'm going to show you that. So we started like projecting and forecasting and like started ringing really the alarm that it could get really bad. So December 19, this is what we had. So the red one, like ignore the red one because that's with Omicron being 3 times as transmissible as Delta, which then quickly we knew that was not the case. So the model estimated Omicron in the island to be 2.6 times as transmissible as the Delta. But the green fit said like at the early January, we're going to look at 4,000 cases for Honolulu or for, you know, and then hospitalization around 250 cases for the beginning of the year for very early January. And here again, that like we shared all our information on the HIPAM, it was publicly available on the website, and then it was shared with the media, with the government. And here again, people were coming to us and sort of suggesting that we're alarmist, and which we were, but that was the reality. That's exactly where we were going. And then let us look at what happened January 18, and let us compare that with the forecasting that we had. So those are, and the students, by the way, Trey, he's also a graduate student in the math department, and he's done those spirals. And it's just another way to look at the data. It displays the exact same data, but one rotation here is 1 year. So in particular, if you have seasonal effect, then you're going to see them very clearly on that type. If you look at the bottom right, for instance, you can see that it's always between like September and October that we maxed the ICU. And so that allows you to look a little bit at that type of effect. So then we also started comparing Delta to Omicron and positivity. That was available, no longer. Positivity is an extremely important indicator of whether we are plateauing, going down. So positivity stopped being releasing as we were going up, but now we are fairly confident that we are on the curve down. So you can see red is Omicron and blue is Delta. So you can see the cases were much higher with Omicron, but the hospitalization were in control and sort of at the same level. But the positivity, if you look here in the middle, that skyrocketed with the Omicron. Now, again, keep in mind, Omicron was deemed to be less severe, milder symptoms, and we have much more people that are vaccinated. So that was a combination. So here is a simulation where I adjusted a little bit. In particular, the red curve was adjusted. It's a cone of uncertainty, okay, that was built in different ways. But if you look, so here, those are basically our forecasting. And then you see the red dots are the actual cases. So it did go the way it was supposed to go based on the model that we developed. And this is where I say it failed. It failed in a sense that maybe not in the sense that that the burden on the healthcare system was too big. It was at the same level that we had for Delta, but we had other byproducts which were in terms like depleting the workforce. People were maybe not going into the hospital. However, they were sick enough so that they couldn't work. So I'm going to accelerate a little bit, but here it's the model did its job. However, I see that a failure because we are where we showed we were and where we did not want it to go. So this is the spiral that represents the COVID death in the state of Hawaii that we have here. So what's next? So we're still in that emergency. We're not at the endemic. We don't know if there'll be another variant. We don't know a lot of that. So, but we have to think about the future. We were completely taken by surprise, like most of us. So pandemic, like now we're thinking about creating pandemic prevention center. And that means trying to fill in the gap, trying to create a multi-scale model that like a lot of the issue with the model was the parameter and the data that were used to fit the model. Okay, so here is you go from the micro scale when you start understanding droplet for viruses and how that works, how the pathogen are via droplets. And then you do computational modeling and you use also PDEs, etc., fluid mechanics in order to grow that from a single droplet to a cloud of droplet to understand transmission between people. And after that, you take that information and you go to a larger scale where you deal not just between two people, but between a population. And then finally, what really needs to be done is protocol for data collection. What type of data do we need? How should they be collected? How should they be shared? All of this should be done before we get into another pandemic. And this is a little bit of a diagram on how the center could look like, like anchored very heavily into the natural sciences, also using engineering for some of the experiments, social behavior, economic science, and then waiting like on education, on outreach, you get the data, and then you get the information to policymaker and to the public. And on the bottom, you have how those different scales, multi-scale with a model that grows as we understand better the virus and we have more information about it. This is again another little scheme on what a pandemic center, pandemic prevention center could do, visioning, using like working with the population, doing workshops, trying to find a good way to talk with stakeholders, partnership with the Department of Health, training the young generation, and doing outreach. And I have two more slides and then I'm done. One big highlight from that pandemic is that we don't have the workforce we needed to do the data analysis. We need data analysts, we need modeler, we need computational savvy people, or computational scientists. We need all that workforce to grow, okay? And one place to grow that is at UH. However, you don't fix at the university level what needs to already be addressed before. So this is just a lot of what we have done in outreach. We need to work with the K-12 schools. We need to infuse that very early on into the youth of Hawaii, and where UH can have a huge role is that our students are very engaged to the community. They want to make a difference. They are very stimulating to the younger generation. So we have all the pieces, we have to bring them together. And then I will finish by saying that we don't necessarily need 100 million influx in order to make a difference. Sometimes small amount can make a big difference. Like by using the workforce we have at UH with the undergraduate student and the graduate student, if I have 15 people that say, okay, I'm going to give $1,000, that's $15,000. I can hire 5 undergraduate students for the entire year. That will go and work with the schools with high native Hawaiian population that were affected by that Red Hill project. This is what we can do. And we don't need $100 million in order to do that. We need people to give some, like, you know, to come together and give a small, maybe smaller amount. Somehow, sometimes it's hard to get the smaller amount. With $100, it's hard to do something. But again, yeah. So that's where I wanted to stop. And then I guess, Alison, I'm giving it back to you.
Thank you so much, Monique. We really appreciate all of your hard work and your dedication. This has been such an extremely important issue that's impacted us all so heavily for the last number of years. So thank you for that. We have opportunities for people to ask questions now. We have one in the chat that I'll read out. And then after that, if anyone would like to unmute their mic and just ask questions directly, feel free to do that. We'll start off with a question from Dr. Virginia Hinshaw. Do the decision makers actually pay attention to the mathematical modeling?
Virginia, it's a very good question. And we hope so. We have indication that it has been done. Now we're not involved in the decision in any policy or anything because it's much more complex than just modeling disease spread. But we do hope so, and we have indication that they were following the work that we were doing, yes.
Hi, I apologize. I was on an errand and signed in a little late. So if you already covered this, just say so. But I was curious about, as a mathematician, when you apply this kind of process to a specific problem, how do you go about coming up to speed in the biology and of this topic? It seems like you could apply these kind of skills to a wide range. So you must really be open to learning new things.
Yes, thank you, Cheryl. This is and this is really highlighting the interdisciplinary aspect of what the pandemic brought up, and that's why. And yes, I said that sort of at the beginning. We formed HiPAM. Dr. Fan, she created HiPAM, and every week we would meet and we will discuss. And there were biologists, there were medical people, there were people from the Department of Health, and then we were able to gather a lot of information because I'm not an epidemiologist, I'm not a biologist, but they were working, we were working together, and everybody was bringing their piece of the puzzle, and they were teaching me what I needed to know for the models.
Was that a first for you, or have you been through that kind of exercise on other topics?
It was the first time that it had to be done in an emergency situation. Usually I have a little more time so I can read the literature, but I have been working with engineers and other people and people from Institute of Astronomy, so trying to learn about the other science, but never on such a short time scale for sure.
So I have a question about when's a good time to actually communicate with the public? It seems to me that during this pandemic, the concepts of transparency versus the concept of actually having enough data to make your model accurate enough to talk about really got mixed up. And in the end, a lot of information was put out, as you pointed out, that made people believe, oh, models don't work. Because the general public just really doesn't understand what it takes to put into a model to actually make it useful.
Right.
So from your standpoint, where do you really start communicating with the public?
Right, Daryl. I like your question a lot because it goes into different directions. So at the time, it was sort of, we were like the simulation became more, the media came more to us to look at the simulation. The model was fairly well advanced and we were fairly well confident about what we were saying. So the issue was not about the modeling and whether it was ready to go out. It was about understanding what modeling can do. And this is really, really hard to convey, right? So I think we're going to learn a lot from what happened with the pandemic and the criticism and how to convey that to the public. And I think there should be some other people than mathematicians that should do that bridge, right? We were sort of thrown out like under the bus. And suddenly the TV and the radio were coming to me and I was like, woo, I don't know. I cannot say that that math say the truth or that numbers are correct, because then it's completely misinterpreted because they're not mathematicians. So it's a big ramping curve. But most importantly, I'd like to branch on your question with the fact that when do you communicate to the public? And it goes with that feedback that the public is given to the communication, right? And that in this case plays such an important role because their behavior changes with respect to the communication, and the behavior is driving the spread. So this is, do you alarm them when when it's going up so that they're a little more cautious, but you try to hide when you're curbing and going down because you don't want them to relax too quickly? I don't know. This is public health people also, and that's a whole great question that is people are starting to look into.
Thank you. That was a good answer. I appreciate it.
We have a couple of other questions that have come in through the chat. Follow up from Dr. Hinshaw. It seems that the Department of Health is releasing less data now. Can you get all the data you need right now for the modeling?
Virginia, we never got all the data we needed, right? We didn't have what was really important to move into Delta and especially Omicron would have some breakdown in terms of who was asymptomatic, who was vaccinated in the hospital, for instance, who was vaccinated, who had the booster, and those type of data we didn't have access. So we had to work with what we had, but indeed they are releasing less data. They are overwhelmed. That's not a Hawaii issue. I think that's a worldwide issue with the data. People were not ready. We have at the same time Mount Everest of data, but not necessarily the one that we need. So this is something that will have to be fixed and understood worldwide. Yeah.
Okay, a second question that's come in from Alexandra B. What do you think will happen with your data when people receive their free COVID home test kits? What are your recommendations?
Oh, that's a great question because now positivity is going to be much less meaningful than it was before. So Alexander, yeah, we're going to have less people detected. That means the daily cases are going to go down. Does it mean less people with Omicron? The latest phase of Omicron, we have based our data on hospitalization. Again, there is a caveat. Are people hospitalized because of COVID, or are people hospitalized for something else and they have COVID? That's also information that we don't have, and that is important to get. So, but that's why we have been overshooting the actual data with Omicron, but we stand by that in a sense that we estimate that the daily cases were not showing everything that was going on, and it will be even less so once they have at-home testing, but there will be good aspect to at-home testing, and we hope that those are going to be even more important than having the data for the modeling. Yeah. But that's a great question.
So we don't have any other questions in the chat right now. Does anyone else have anything they'd like to ask of Dr. Chyba?
So I'd like to highlight the students. They've been phenomenal throughout that experience, and absolutely nothing of this would have happened if it wasn't for them. They were the driving force, the powerhouse behind, and I kept them hidden for a very good reason. And they know that I talk to them, it's because it's a controversial subject, and I've got some manifest in the mail, I've got some emails that I do not want go to the students. So it was decided very early on that the students would stay in the background, but really they're the star of everything that happened with the modeling. And a few of them are here, so really kudos to them.
Fantastic. Well, thank you. We will end our Q&A session at this point. I'd like to extend a final thank you to Dr. Chyba for her presentation today. That was really fabulous. And also thank you all for attending. It's good to see you all. Happy New Year. We look forward to seeing you all soon. Our next event is planned for Wednesday, February 9th at 2 p.m. HST. It's going to feature Dr. Shadia Habal from the Institute for Astronomy. She'll be speaking on the scientific magic of total solar eclipses. So watch your inboxes for your invitations to this event. Thank you again, Monique, and thank you all
so much.
Aloha.